Hello, everyone. I'm Rahul, a PhD student at the Indian Statistical Institute in Kolkata, India. My research mostly revolves around the rising tensions and anomalies in cosmology, and my focus is on exploring various statistical and machine learning techniques in this context, including both model dependent as well as independent investigations. So today I shall be talking about revisiting the cosmic distance ladder with deep learning approaches, and we'll see some prospective applications of the same. So any investigation of the universe should in principle be free of biases and must be driven by cold hard observations. Of course, it's not always possible to have a purely data-driven approach given technological limitations, but we should try our best with the data available. This is perhaps the primary motivation behind the work I'm going to present. Now, I'm pretty sure the audience here needs no introduction to this, so I'll just say that this is our present understanding of the universe, where we are sitting here on the right and trying to understand our history by looking farther and farther back in time. But how do we actually go about doing this? Well, we mostly measure distances and also try to study patterns on the sky. But I'll be concerned with measuring distances for the purposes of this presentation. So you then go outside with your telescopes and measure distances in different ways, and then make inferences on cosmological parameters. Since we have one universe, and assuming that the experiments have all been done correctly, we should expect unique values of the cosmological parameters. But we do not get so. Instead, we end up with the extremely well-known cosmological tensions like the Hubble tension and the clustering tension. The reasons for this could be multiple. Number one, it could be due to systematic errors in one or more experiments, or perhaps physics beyond the baseline lambda cold dark matter, the lambda CDM model, is required. Or it could be due to correlated biases and miscalibration between datasets, or a combination of all of the above. So for the moment, let's say there are no systematic issues in the datasets, and say I want to infer on cosmological parameters without assuming any particular cosmological model. That is, we want to take a purely data-driven approach. Now, there are many ways to do this. You could do cosmography, but then you need to figure out where you would truncate your series. Or you could use some parametric forms, but then your results may be biased by the exact choice of your form. So, if we are to follow Reach's advice, we should adopt non-parametric methods. Now, multiple authors have written even more multiple papers on how to do this using various techniques, including various machine learning algorithms. Here, I'll demonstrate the use of deep learning networks for non-parametric reconstruction of cosmic history. So for now, you need not be bothered by exactly how a deep learning network works, but you need to understand what they do. They are universal function approximators. So if you train a network with data derived from an unknown function, then no matter the function, in principle, the network should be able to learn and approximate it. It's basically just regression on steroids. So we are not the first ones to use deep learning in cosmology, and there exists a wide range of learning models in the literature. But there are some limitations which were more or less generic to all of them that we wanted to somewhat overcome with ladder. So there existed overfitting and underfitting issues. Moreover, since our aim is to do precision cosmology, we want to have reliable predictions of error bars and uncertainties as well. And finally, we want to be able to make reliable predictions at extrapolated redshifts, maybe even beyond the available data range or even in regions where data is sparse. So we came up with the aptly named ladder framework in collaboration with machine learning experts here at ISI. So in principle, any sequential dataset with covariance information could be used to train ladder. But here we train it with the uncalibrated Pantheon supernovae compilation, which gives data for the apparent magnitude of around 1048 type 1a supernovae along with the 1048 cross 1048 covariance matrix. Now, given the Gaussian nature of the data, we make use of the KL divergence metric as a loss function to train, test, and ultimately validate ladder. So this is a very rough pictorial representation of how ladder works, but let me try to explain more intuitively how this framework differs from traditional networks used in cosmology. So in a normal application, data is fed into the network one by one, often with no information from the covariance matrix or utilization of the sequential nature of the dataset. Instead, here we make use of long short-term memory, or also called as LSTM networks, which are optimized for sequential data. And we incorporate the covariance information as follows. Say we take about 30 data points at random, where 30 is for now an arbitrary number. And we construct a kind of a multi-dimensional Gaussian distribution with these by taking into account the uncertainties as well as the corresponding covariance matrix. We then sample from this distribution, feed it into the network, and ask it to predict the 31st point. And we keep doing this again and again and again, random every time. So this helps in injecting the uncertainties into the training process. And as a result, we see that the reconstruction is relatively stable and it has some decent extrapolation capabilities as well, which I shall discuss soon. But coming up with a fancy algorithm is all well and good, but it doesn't mean anything unless we can do proper validation tests. So we chose the optimal ML configuration amongst different methods, and we judged them on the basis of certain physical parameters, which we expect to be true in the case of the distance modulus dataset, namely monotonicity and smoothness, and of course the accuracy in the predictions. We also do a grid search to obtain the optimal network configuration. Now, you may choose to not listen to the rest of my presentation, but please take home this one very important message. And that is that robust validation metrics must always be used when applying any machine learning model to cosmology, without which trusting any predictions is perhaps not wise. With that being said, and that little anecdote for you. So we move on to the first application with this trained network. So we asked Ladder to make predictions. Now Ladder has been trained with Pantheon, and we asked Ladder to make predictions at Pantheon plus redshifts, which is the immediate successor of Pantheon and something Ladder has never seen. It has a higher data density at lower redshifts compared to Pantheon. Some concerns were also raised regarding Pantheon Plus, for example, overestimation of errors or perhaps uncorrected systematics. With Ladder, we are trying to investigate these concerns in an entirely model-independent way. So visually, we see that the blue ladder reconstruction nicely traces the expansion history, but to see this more qualitatively, we obtain constraints on the lambda CDM and WCDM model for three different datasets: Pantheon, Pantheon Plus, and ladder predictions at Pantheon Plus redshifts. We see that the ladder results trace the Pantheon results, which implies a good reconstruction in the case of both models. The constraints vary slightly for the three datasets, but we find them to be consistent within the 1 sigma confidence level. Now, moving on to the second application, we wanted to see if we could calibrate high redshift datasets, such as gamma ray bursts, in a model-independent way by using ladder. Turns out we can. So the way we did this, we used the GRB A219 sample, which has been split into two parts, a low redshift and a high redshift part. For the low Z samples, we cross-correlated them with ladder reconstruction and made use of the Amati relation to obtain the GRB calibration parameters. We then extrapolated this dataset to higher redshifts, and as a result, we have a unique model-independent calibrated GRB dataset. When I say model-independent, I mean cosmological model-independent. Now, to compare the ladder calibration with the standard lambda CDM-based calibration, we obtain the constraints for two different models, lambda CDM and WCDM, the same as the last application. And we find that the constraints obtained on the model parameters are consistent irrespective of the calibration method used. However, the main takeaway here is that ladder enables us to calibrate such high redshift datasets in a purely data-driven approach. Right. For the third application, we wanted to calibrate baryon acoustic oscillation datasets with ladder. So ladder makes predictions on the apparent magnitude, and bow datasets essentially give distances if you know the co-moving sound horizon scale. Now, given the degeneracy between the supernova absolute magnitude and the co-moving sound horizon, we take the help of anchors. On the one hand, we take an astrophysical prior on MB, and on the other, we take the lambda CDM Planck based prior on RD. And we do this for transverse and anisotropic bow datasets. And we find in a very model independent manner that regardless of the anchor used, the angular bow MBRD parameter space overlaps, but the anisotropic case does not. So there seems to be some sort of inconsistency between angular and anisotropic bow datasets. Now, this is indeed a known issue, but what I'm trying to demonstrate here is that this finding is not any cosmological model dependent, since we are using ladder, which is completely data driven. Moreover, if we include the error predictions from ladder, we are led to a purely data driven selection in the MBRD parameter space, which can perhaps be useful in ruling out some alternative cosmological models, of course, given ladder's precision. Now, for the final application, let's go back to these. So these are the primary data sets used in cosmological parameter estimation. For bow specifically, the information about distances is obtained by injecting RD, which is dependent on the cosmological model assumed. Now, we wonder, what if we calibrate bow with ladder, as in the previous example, with an astrophysical prior on MB? Mind you, an astrophysical prior, not a cosmological prior, which is, of course, cosmological model dependent, independent. Now, the motivation is merely to decouple any model dependence or potential CMB bias into the bow dataset. So we then try to constrain cosmological parameters with supernovae, CMB, and this recalibrated bow dataset. We do this and get constraints like this. Now, we see that ladder calibrated bow datasets cause an in-plane shift in the H0 S8 parameter space, such that both tensions seem to be relaxed. So, have we solved the Hubble unclustering tensions? Maybe, but what I must stress is that the motivation for recalibrating bow was not to solve tensions, but rather to follow Reach's advice, that is to maintain independence of the different data sets and try to reduce bias. By using ladder, we practically eliminate the lambda CDM and CMB bias from the bow dataset by reconstructing the cosmic distance ladder in a very, very model independent way. And of course, as a happy ending, we see that the tensions seem to be relaxed, all within the lambda CDM framework, which is good because recalibration does not end up giving wildly undesirable results. So here I'll summarize the key takeaways. The possibility of overfitting and underfitting issues in deep learning can lead to inaccurate and imprecise predictions in the context of cosmology. Hereby, we propose ladder that can learn sequential data utilizing the full covariance information within the data points. Reconstruction with ladder also exhibits stability even in data sparse regions that can give reliable predictions beyond the training data range, which can have one prospective application as, for example, model independent mock data generator, for example, to generate mock gravitational wave data sets for forecast studies in the context of some future GW mission. Finally, we do not claim that ladder is the final word in deep learning reconstruction in cosmology, but given its very unique potential, we hope this will open up new avenues for exploration in this direction in the future. Well, ladder is now public and available on my GitHub page, so I welcome everyone to use the code, play with it, and modify it as you see fit. I also encourage everyone to have a look at the corresponding papers, which contain more details of the work presented here. One is published in the Astrophysical Journal supplement series, and the other one is currently communicated. So before I end, I really want to thank the organizers for this lovely opportunity. And I very much look forward to hearing your opinions and suggestions, if any. And I'll be trying my best to answer any questions that you may have in the discussion sessions. So thank you.